so this is our honors chemistry lesson video for section 10.1. And so in chapter 10, we are going to start talking about a new unit of measurement called the mole. So you often measure the amount of something by count, by mass, or by volume. So for example, like by count, you buy eggs by the dozen. So you buy a pack of 12 eggs, so that's measured by count. By mass, sometimes when you buy produce at the grocery store, like apples and things like that, you put them on the scale so you can get the mass and then you're charged per pound or something like that. Or by volume, so that's how we buy a lot of our drinks, like we buy a 2 liter of Coke, and so that's measured by volume, or sometimes they'll say 500 milliliters or something like that. So a mole, which has the abbreviation MOL, of a substance is 6.02 times 10 to the 23 representative particles of that substance. So this is 602 and 21 zeros. So this is a gigantic number. The reason it's so large is that atoms are so small. So even though this number is huge, I can hold this number of atoms in the palm of my hand. So 6.02 times 10 to the 23 is just called Avogadro's number. And so we can use it as a conversion factor. So 1 mole equals 6.02 times 10 to the 23 representative particles. Now when we say representative particles, what we mean by that is it could be atoms, molecules, or ions. So those are the types of representative particles we mean. So how do you know which one it's going to be? Well, a representative particle refers to the species present in a substance, so it's usually atoms, molecules, or ions. And so elements normally exist as atoms, but 7 elements exist as diatomic molecules. And those are H2, there's a 2 here, sorry, there's a snowflake in the way. N2, O2, F2, Cl2, Br2, and I2. So these elements, when they're by themselves, they exist paired up as diatomic, so 2 of them bonded together. Now once they bond with something and make a compound, they don't have to have the 2 subscript anymore. It just depends on what they need to make the compound stable. But when they're by themselves, they have the 2. So here's the difference in an atom, a molecule, and an ion. An atom is just one thing. So Be is an atom. Ag is an atom. K is an atom. A molecule is more than one atom bonded together. So H2O, there's 2 hydrogens, 1 oxygen. These are molecules. Br2, that's 2 Br atoms. That would be a molecule. HCl is a molecule. And then an ion, you will see a charge. So here we have Na with a positive, so that is an ion. Cl negative is an ion. O with a negative 2 is an ion. SO4 negative 2 is a polyatomic ion. And so that's how you can tell whether you're working with atoms, molecules, or ions. So the most important one that people forget are the 7 diatomics. And the easy way to remember them is, if you look at the periodic table, if you start at element number 7, which is N, and you draw a big 7 with your finger, you'll see NOF, and then as you go down, you'll see ClBri, and then you just have to remember hydrogen, which is on the other side of the periodic table. So let's look at what a question using our new conversion factor would look like. So it says, how many moles is 2.8 times 10 to the 24 atoms of silicon? All right, so as always, we start with what we're given. So we have 2.8 times 10 to the 24 atoms of silicon. And then we just follow our golden rule like we've been doing all year. My golden rule says if I have atoms of Si on top, I need atoms of Si on bottom. Now the important thing is, notice I'm not just writing atoms, I'm writing the substance. Once we get to stoichiometry, the substance is going to change. And so you're not just matching the unit, you're also matching the substance. So in this chapter, just go ahead and get used to writing the substance, so that way it's second nature by the time we get to stoichiometry. So 1 mole is 6.02 times 10 to the 23 atoms, molecules, or ions. Since I need atoms on bottom, my 6.02 is going to go on bottom. So 6.02 times 10 to the 23 atoms equals 1 mole. So see, my atoms cancel. And as always, because one number is on top and one's on bottom, we're going to divide by this. Now you need to be careful when you put this in your calculator. Depending on the way you type it in, you may need to put this whole thing in parentheses. just like that, because otherwise it'll divide by the 6.02 and then it'll actually multiply by the 10 to the 23, and you need to divide by the whole thing. But again, that depends on how you type it in and what calculator you have. So just make sure you're getting the same answer as I am. So for this one, what I got was 4.65, and then my unit is moles, and my substance is SI. Just like that. All right, so again, what determines whether the 6.02 goes on top or on bottom is following the golden rule with your units. So let's look at some more. All right, so if you're comfortable, go ahead and try one on your own, but if you're not, you can watch me do this one and then try this one on your own. So it says, how many moles is 2.17 times 10 to the 23 representative particles of bromine? So see here, they didn't tell me whether or not the representative particle is an atom, molecule, or ion, so I'm going to have to figure that out myself. All right, so we start with what we know, and that's 2.17 times 10 to the 23, and then I have to figure out what my representative particles are. Well, bromine on the periodic table is Br, which may make you think, oh, it's an atom. However, it's one of the 7 diatomics, so it's actually Br2. So it's actually a molecule. Okay, and that becomes important in our answer. All right, so I have 2.17 times 10 to the 23 molecules of bromine. All right, so I need molecules of bromine to go on bottom because I'm following my golden rule. And so if I look at my conversion factor, molecules goes with the 6.02 times 10 to the 23. So the 6.02 times 10 to the 23 is also going to go on bottom. And that, of course, equals 1 mole of Br2. So my molecules of Br2 cancel because one number's on top and one's on bottom. I'm going to divide again, and I got 0.36 moles of Br2. So see, this is where it comes into play. In my class, if you put 0.36 moles of Br, I count that as an incorrect unit, and that's half off. So you don't want to lose half over a little 2. Okay, so make sure you always remember your 7 diatomics. All right, so I'm going to assume that you pause the video and try the next one, and then we'll look at it together. So it says how many molecules are in 2.12 moles of propane? And then I tell you molecules is M/C. That's the abbreviation for molecules, just like I did up here. All right, so first thing is you may need to know what propane is. Propane is C3H8. So if you weren't sure of that, you might have just written the word propane instead. And so then we just start with what we know. So we have 2.12 moles of propane, which is C3H8. And so then we follow our golden rule. This time, because moles is on top, I'm going to put my moles on bottom. So how many moles? Well, it's 1 mole. All right, so see, that's the problem. Some of you, once you see me do 2 of them and you see me put the 6.02 on bottom, you're tempted to do the same thing. But remember, you always follow the golden rule. So 1 mole is 6.02 times 10 to the 23 molecules of propane. So my moles cancel. Since both my numbers are on top this time, I'm going to multiply, and I end up getting 1.28 times 10 to the 24. My unit is molecules, and my substance is the propane, which is C3H8, if you didn't already know that. All right, and so this is how you use this conversion factor. Now, we're going to learn more conversion factors for the mole throughout this chapter, but this is the one that we'll focus on for this section. All right, now sometimes they're going to ask you a question, and it's going to seem like there's a typo. Okay, and so let me show you how there's not a typo, there's just an extra step. So it says how many atoms are in 1.14 moles of SO3? Well, the thing is, SO3 is a molecule. It's not an atom. But this isn't a typo. Like it's not like it was supposed to say how many molecules. It means that we need to take into account that there are 4 atoms in this molecule. So I'll show you what I mean. Let's go ahead and start it. So we start with our 1.14 moles of SO3. Y'all, when in doubt, just always start with the number I give you and try to work your way from there. All right, we're gonna follow the golden rule. So since mole is on top, mole is gonna go on bottom. How many? Well, it's always 1 mole equals, and then our 6.02 will go on top. But remember, we decided SO3 is a molecule, not an atom. So I'm going to put molecules of SO3. Again, that's the important thing. If it's a molecule and not an atom, you can't just call it an atom. But it asks me for atoms. So I have to take into account that 1 molecule of SO3 is actually 4 atoms. Because see, we have 1 S and 3 O's. So it's actually 4 atoms. So I have to then do another step where I say 1 molecule of SO3, because again, I'm following my golden rule, molecules of SO3 equals 4 atoms. Now notice I didn't write atoms of SO3 because it's atoms of S and O, so at that point I would kind of drop the substance. So in other words, once you get your answer, you just need to multiply it by the fact that you have 4 atoms. So I multiplied all 3 numbers since all 3 were on top, and I ended up getting 2.75 times 10 to the 24 atoms. See, this is where you just have to be careful. Okay, make sure you carefully read the question. If they gave you a molecule, but yet they're looking for atoms, you have to do this extra step. Now, if they had just asked you about molecules, you would have stopped right here when you got to molecules. All right, so let's look at a couple more. Alright, so it says, how many moles are in 4.65 times 10 to the 24 molecules of NO2? Well, NO2 is a molecule. It didn't ask me about atoms, so I don't need to do any extra steps this time. Alright, so I start with what I know, and I know I have 4.65 times 10 to the 24 molecules of NO2. We are trying to get to moles, so I know I'm using my conversion factor. And so I follow my golden rule. I have molecules on top, so I'm going to put molecules on bottom. And so the 6.02 goes with atoms, molecules, or ions. So I'll put my 6.02 on bottom and my 1 mole on top. So see, my molecules cancel, and since 1 number's on top and 1's on bottom, I'm going to divide this time. And so when I divided, I got 7.72 moles of NO2. Just like that. All right, so maybe pause it. You try the third one. I will go ahead and give you fair warning. I gave you magnesium sulfate, which is a compound. But yeah, I've asked you how many atoms. So you are going to have to do that extra step I showed you on the previous slide. So I'm going to assume you paused the video and you've tried this on your own, and now we'll look at it together. So it says how many atoms are in 4.33 moles of magnesium sulfate? Well, the first thing I need to do is figure out, well, what is the formula for magnesium sulfate? So magnesium is Mg. It has a positive 2 charge. Sulfate is SO4. It has a negative 2 charge, so I don't need to cross charges or anything. So the formula is MgSO4. So see, I can clearly see this is more than 1 atom, and since it asked me about atoms, that's how I know I need to do that extra step. All right, so I start with what I know, which is 4.33 moles of magnesium sulfate. And so first step is, of course, I'm going to have to go to molecules, and then I can go to atoms. So I follow my golden rule, and my mole is going to go on bottom. And so, of course, it's just the 1 mole, and that equals my 6.02 times 10 to the 23. We'll call it molecules, but really it's kind of ions of magnesium. Well, it's an ionic compound, but for now we'll just call it molecules. Really, it's ions that have been bonded together, and one's a polyatomic ion. But like I said, for now we'll just call it a molecule, but just know it's not actually a molecule. It's an ionic compound. So then I have to get to atoms. So I have to look at how much this contains. So one, what we're calling molecule of magnesium sulfate, really is an Mg, an S, and 4 O's. So it's actually 6 atoms. So then I would follow my golden rules to see my moles went away, and I have molecules on top, so I would put 1 molecule of MgSO4, which again, it's not a molecule, it's actually an ionic compound, is 6 atoms. So then because all three of my numbers are on top again, I'm going to multiply. And so when I multiply, I got 1.56 times 10 to the 25 atoms. So the important thing is make sure you can use the conversion factor, and then make sure you realize when you need to do that extra step and when you don't. Okay, and so you mainly need to do the extra step if I give you more than one atom in the formula, but then I ask about atoms. Alright, so let's look at another one. So this says calculate the number of H atoms in 0.35 moles of C6H12O6. So this one's slightly different because we're only worried about the hydrogens. We're not worried about how many atoms are in the whole molecule. We're just worried about hydrogen. So I'll show you how to do this one. So we're going to start with what we know, of course, and that's moles. So we have 0.35 moles of C6H12O6. We're trying to get to H atoms, hydrogen atoms. So first, I know that C6H12O6, though, is a molecule. So I'm going to have to go from moles to molecules first using my conversion factor. So I follow my golden rule, and I'm going to put mole on bottom. So I put my 1 mole C6H12O6 on bottom, and that equals 6.02 times 10 to the 23 molecules on top. Okay, as much as you may want to say atoms at this point, it's not. And so then from here, whereas in the previous questions I would have said, okay, well, one molecule is actually 24 atoms because I would have added up all of them. We're only worried about the hydrogen atoms. So I can say that one molecule of C6H12O6 contains 12 hydrogen atoms, since they only asked me about hydrogen atoms. So then, once I know this, I can follow my golden rule. The molecule will go on bottom, so one molecule of C6H12O6 is 12 hydrogen atoms. So my molecules cancel. Since all three of my numbers are on top, I'm just going to multiply across the top. And so I end up getting 2.53 times 10 to the 24 atoms of hydrogen. And so see, in this case, it's just slightly different than what we just did, because instead of asking me for atoms in total, it just asked me about one of the elements. And so all I did was just pull that one element out. So hopefully, super easy. Really, it all comes down to how good you are at converting. If you're good at converting and doing dimensional analysis, which is using the conversion factors, then this is probably pretty easy. Okay, so if you feel confident, you can go ahead and try part A. Otherwise, we'll look at it together. So how many oxygen atoms, so notice it's just asking me about oxygen atoms, are in 0.25 moles of CaNO3 2. Now again, this is an ionic compound. It's not really a molecule, but just for the sake of using our units that we have over here, we'll just call it a molecule right now. We can't really call it an ion because it's also made of multiple ions. So it's not like it's just one ion. But anyway, so let's start with what we're given. So 0.25 moles of CaNO3 2. So my first step is to get to what we'll call molecules. Like I said, this is really an ionic compound though. So I follow my golden rule. So I need the mole on bottom. So 1 mole of CaNO3 2 equals 6.02 times 10 to the 23 molecules of CaNO3 2. So my moles cancel. But they didn't want to know how many CaNO3 2 I have. We want to know how many oxygen atoms. So if you look, because the 3 and the 2 both go to oxygen, one molecule of the CaNO3 2 equals 6 atoms of oxygen. Okay, because the 3 and the 2 both go with oxygen, so it's 6. So then I just follow my golden rule. So one molecule of CaNO3 2, which again, it's not actually a molecule, it's an ionic compound, equals 6 atoms of oxygen. So my molecules cancel, and then since all 3 of my numbers are on top, once I'm done, I just multiply. So I got 9.03 times 10 to the 23 atoms of oxygen. Okay, so if you didn't try this one, pause it, try this one. The thing is though, make sure you get the formula right before you try it. If If you miss the formula, you're going to get the wrong number of oxygen atoms. All right, so I'll assume you tried this one on your own. So it says how many oxygen atoms are in 1.5 moles of sodium carbonate. Now this again is an ionic compound, but we'll just call it molecules for right now for the sake of being able to cancel out our units. All right, so sodium carbonate. First I have to write the formula. So sodium is Na with a positive charge. Carbonate is CO3 with a -2 charge. So I would cross my 2. So I can see now that there are 3 oxygen atoms in a formula unit of sodium carbonate. All right, so we start with what we know, which is 1.5 moles of our sodium carbonate. So see, for this one, if you forgot to cross your charges, you'll actually still end up getting it right since they just asked me about oxygen. But if they had asked me for total atoms, if you did not remember that you needed 2 sodiums, you would miss it. So make sure you're careful on getting your formula right. All right, so I follow my golden rule, and I'm going to put moles on the bottom. And so how many? Well, my conversion factor says 1, and that equals 6.02 times 10 to the 23. And like I said, we'll call it molecules, but please know this is an ionic compound. It is not made of molecules. And so then our next step, though, is we got to get to oxygen atoms. So I can look and see that one formula unit or molecule of Na2CO3, even though remember it's not an actual molecule, has 3 atoms of oxygen. So I just need to follow my golden rule again, put my 1 molecule on bottom, even though again it's not an actual molecule, and then that makes 3 atoms of oxygen. So then my units cancel. Since all my numbers are on top again, I'm going to multiply again. So I get 2.71 times 10 to the 24 atoms of oxygen. Just like that. So hopefully you're getting these right. Like I said, you got to know how to use these formulas. All of Chapter 12 is going to be about using the formulas you learn in Chapter 10. So if you can't use these conversion factors, you're really going to struggle in Chapter 12. Alright, so the next thing that we learn in the first section of Chapter 10 is molar mass. Okay, so we learn how to use this conversion factor, and then we learn how to calculate molar mass. So the atomic mass of an element expressed in grams is the mass of a mole of that element. So normally when we look at the periodic table, the mass has a unit of AMU, atomic mass unit. However, in lab, we don't have scales that measure AMU. We have scales that measure grams. So the convenient thing about a mole is if you have a mole of the substance, it has that same mass but in grams. So instead of using AMU from now on for our mass, we're going to use grams instead, because that's of course more convenient in the lab. And also in the lab, we're not usually working with 1 or 2 atoms at a time. We're working with billions, even if you have a super small sample. So the mass of a mole of an element is called the molar mass. So molar mass is just the mass of 1 mole of a substance. It is also called the molecular weight. So sometimes you'll see it called molecular weight, sometimes you'll see it called molar mass. They mean the same thing. To calculate the molar mass of a compound, you find the number of grams of each element in 1 mole of the compound, then add the masses of the elements in the compound. So it's super easy when you have the formula. Okay, so it says, what is the molar mass of PCl3? I'm going to round all the molar masses to whole numbers from the periodic table. You're more than welcome to go out decimal places though, but for ease, I'll use whole numbers in class. So P ends up being about 31, so all you do, y'all, is you look at the periodic table, just to let you know where this is coming from. We have P, it has the 15 up here, and it has like 30.97 something on the bottom. This is where I'm pulling the numbers from, so I'm going to round that to 31. So P is 31, Cl is about 35, again it's 35.4, so that rounds to 35, but I'm going to multiply it by 3 because I have 3 of them. Okay, so in other words, literally I'm just going to do 31 plus, and then 3 times 5. And so once I do that, I end up getting 136. Now the unit for molar mass is grams per mole. Because remember, molar mass is the mass of 1 mole. So it's only 136 grams if you actually have 1 mole. So that's why we say grams per mole. So be super careful about your unit. I do not count grams as the correct unit. I do not count moles as the correct unit. It's got to be grams per mole. All right, now the trouble that happens, because I know some of you are probably like, oh my gosh, this is so easy. That's what everybody thinks. The problem is I don't normally give you the formula. I give you the name. So you've got to be able to write the formula. So if you struggle with writing formulas, you're going to struggle with molar mass. All right, so see, this is what you would see, like on a test or quiz in here, is the name of the substance. All right, so let's look at the first one together, and then I'll let you try the second one. So the important thing is you have to get the formula right to get the molar mass right. So it says, what is the molar mass of sodium hydrogen carbonate? Well, sodium is Na, and it's positive 1. Hydrogen carbonate is one of your polyatomic ions. It's HCO3 negative 1. So if you look, my charges are already balanced. So then I just will look at each element. So my mass for sodium, so you just find on the periodic table, is about 23. My mass for hydrogen is about 1. My mass for carbon is about 12. My mass for oxygen is like 15.99, so I'll round that to 16. And then I'm going to multiply that by 3 though, because I have 3 oxygens. So once I do all that, I get about 84. And then because I just calculated molar mass, my unit is grams per mole. So like I said, if you mess up the formula, then you're going to mess up the molar mass. All right, so maybe pause the video and you try this one, and then we'll look at it together. So it says, what is the mass of calcium nitrate? Well, calcium is Ca. It has a positive 2 charge. Nitrate is NO3. It has a negative 1 charge. So I need 2 nitrates. So I put it in parentheses like this. So this is where you got to be careful. When you get parentheses, sometimes you'll have trouble figuring out how many atoms. So I'll look at the periodic table. Calcium is about 40. Nitrogen is about 14, but I have 2 nitrogens. This 2 outside the parentheses goes to the N and to the O. So I multiply that by 2. I have 16 for oxygen, but if you look, I have 6 oxygens because the 2 and the 3 go to oxygen. And you multiply, don't add. It doesn't make 5, it makes 6. So you're multiplying. So once I add all of those together, I get 164, and of course my unit is grams per mole because we are calculating molar mass. All right, so hopefully you find that pretty easy. Like I said, the main thing people struggle with is getting the correct formula to start with. If you need more help on doing formulas, then go back to Chapter 7 and Chapter 9. All right, so section assessment. It says, describe the relationship between Avogadro's number and 1 mole of substance. Well, they're equal to each other. 1 mole is 6.02 times 10 to the 23 representative particles. And remember, representative particles includes atoms, molecules, and ions. So number 2, how can you calculate the mass of 1 mole of a compound? Well, that was molar mass. We just add the masses of each element. Add the masses of each element. All right, number 3, it says how many moles is 1.5 times 10 to the 23 molecules of NH3? Well, I can see that NH3 is a molecule. It has more than 1 atom, so it is a molecule, so I don't need that extra step. I can just use this conversion factor. So I start with what I know. So I have 1.5 times 10 to the 23 molecules of NH3. And so I follow my golden rule, and I put molecules of NH3 on bottom, and NH3 really is a molecule. And so I put my 6.02 with that. And that, of course, equals 1 mole of NH3. So my molecules cancel. Since one number's on top and one's on bottom, I'm going to divide. And so once I divide, I end up getting 0.25. Then my unit is mole, and my substance is NH3. And so again, because it didn't ask me about atoms, I don't have to do that extra step. Since it asked me about molecules, and NH3 is a molecule, I didn't have any extra steps on this one. All right, so number 4, it says how many atoms are in 1.75 moles of CHCl3. So this is an extra step one, because see, it gave me atoms, but CHCl3 is a molecule, and it's not ionic, so it actually is a molecule this time. All right, so this is where I'm going to have that extra step. So I start with what I know, and that is 1.75 moles of CHCl3. So my first step is to use my conversion factor, and I'm going to get to molecules because CHCl3 is actually a molecule. So I follow my golden rule, and I'm going to put the mole on bottom. So 1 mole of CHCl3 is, of course, 6.02 times 10 to the 23 molecules of CHCl3. But the problem is, of course, it asks me about atoms. So I can look at CHCl3 and I can see that 1 molecule of CHCl3 is actually 1, 2, 5 atoms. Because there's 1 C, 1 H, and 3 Cl. So I follow my golden rule, and I'm going to put the 1 molecule on bottom and the 5 atoms on top. So look, my moles cancel, my molecules cancel. I'm left with atoms, which is what it asked for. And so then I just multiply across the top since all 3 numbers are on top. And I got 5.27 times 10 to the 24 atoms. Just like that. All right, and then the last one. This one's super easy because I actually gave you the formula instead of making you write it yourself. So it says, what is the molar mass of calcium sulfate, or CaSO4? So I find calcium on the periodic table is about 40, sulfur is about 32, oxygen is about 16, but I'm going to multiply that by 4. So once I do all that, I end up getting about 136, and then our unit for molar mass is grams per mole. Alright, so like I said, out of section 10.1, the 2 important things are that you can use this conversion factor and you can do molar mass. Alright, and then in section 10.2, we will use molar mass a little bit more.